In our introduction, we discussed some of our main problems, our hypotheses which involve transmitted light and emitted fluorescent light, and our results in which we discovered that we have Lapidus dye. Our background of knowledge included our knowledge that we knew regarding solutions, which we know has a fingerprint absorption spectra that can help scientists determine a solution's composition and concentration. We also knew about Beer's law, which states that absorption is directly related to concentration. Essentially, this law states that the absorbance of a light-absorbing material is proportional to its concentration in solution, and this is seen through our various equations. On the left side of the slide, this is the setup that we used in class. On the top right, this was what was occurring on a molecular level, and on the bottom right, the spectra seen is similar to what we saw in the emission spectrum in class.
To measure the intensity of transmitted wavelengths, we used a fiber optic cable and ocean optics software. We measured light through a 1 centimeter cuvette in a dark room to eliminate any outside light contaminating our measurements. We had 3 cuvettes, one with water, one with our unknown dye, and one with our fluorescent dye. We used Excel to create the absorption graphs for each solution, as well as a fluorescence graph. We used the calculated absorbance to identify the dye's concentration and its name. To measure absorption, we measure the light straight through the cuvette. For fluorescence, we have to measure at a 90-degree angle to record the emitted light from the fluorescent dye and to avoid recording the transmitted light from the flashlight. This could have led to some possible errors, like recording transmitted light instead of emitted light and the light from the external environment.
To determine the identity of our unknown dye, we compared the absorption spectrum of our dye to that of our unknown dyes. Given that our dye and the Lapidus both have peaks at 560 nanometers, we can confirm that the identity of our unknown dye is the Lapidus dye. To calculate the absorption, we used the equation seen in the middle top provided to us in the Beer's law activity. We found that our peak absorption was 1.2385 liters times inverse moles times inverse centimeters. We can then rearrange Beer's law to solve for concentration. Specifically, concentration will equal the absorption over the quantity of the extinction coefficient times the path length. By doing this, we determined a concentration of about 2.9 times 10 to the negative fifth moles per liter. It's important to note that we calculated concentration and absorption for each individual data point and used the maximum values. Fluorescein, we can see our data on the top compared to the theoretical data on the bottom. We found that our data is incredibly similar to what was expected, but it's important to note that our graphs appear shifted to the right. This may possibly be due to the redshift phenomenon.
Absorption spectra is obtained by transmitting light through a substance, whereas fluorescence is a spectrum of light emitted by a substance when excited. We can use absorption to determine the composition of a solution or a distant star, and we can use fluorescence to tag different proteins with different fluorescent dyes to determine their presence or functionality. We observed a certain wavelength photon at 525 nanometers enter the fluorescent dye, excite electrons from their ground state, and photons of a different wavelength at 550 nanometers are emitted as the electrons fall back to their ground state. In other words, the emitted photons are of a lower energy than the absorbed photons. According to the law of energy conservation, this lost energy is still conserved as it is transferred into kinetic energy of the molecular vibrations while the molecule is excited. The energy is eventually released as heat as the molecule falls to its ground state.